It's just at the end of
I just know them.
It's not that.
There were nothing. There is a few.
It's like a lot.
I mean, it's like, you know, like that. And then. They're looking closer.
Oh, yeah.
Except they said two ship. I was there, is this something and then I realized that like Sarah got like bunch of Sarah. I have one.
Okay, can you turn to page 5?
That was pretty good, Chester.
That's, you go ahead. So I just think
So today's topic is linear approximation. I don't think this will take the entire class, so I think it would be good if we can start related rates today, since that takes a little more time to get used to. So once we get past the notes, we're going to just try to get ahead. I'm not going to change the calendar in terms of homework assignments. Homework assignments will stay the same, but if we can get ahead, then we just buy an extra day of review when we get to the end. Okay, so the tangent line of a function f of x at x equals a can give you an approximate value of the function of a point that is close to a. So let's say our graph looks something like this. Okay. And let's say there was a x value of 6, and you created a tangent line at 6. So let's say you found the slope and you found the order pair, and you created a tangent line equation. Now, let's say let's say the graph is called f of x, and let's say the tangent line is called y of x. Okay. And let's say we wanted to use the tangent line to approximate a value on this curve. Let's say we wanted to approximate, let's say f of 6.1 is somewhere here. But then the tangent line, if I plug 6.1 into the tangent line, it's going to give me this value. Right? Obviously, it's not going to be the same because it's approximation. Any point that is off of the tangent is going to be different. But because the graph is concave up and our tangent line is below, what do you know about our approximation? Is it going to be over or under approximating the actual value? Under, right? So that's the basic theme here. We're going to create the tangent line, but if we know that our graph is concave up, it doesn't matter where our tangent line is. Our tangent line is always going to under approximate our curve because our tangent line is always going to sit below the curve. Meanwhile, if I have a graph that's concave down, and if I create a tangent line, anything that is on the tangent line is going to do what? Overestimate. Yeah. So that's the big thing here. If we know the shape of the graph and we create a tangent line, our tangent line is always going to either under approximate or underestimate for a graph that's concave up versus a tangent line that will always overestimate or over approximate the actual point on the graph. So I hope this is not something that we have to memorize because I think if you can just quickly sketch a graph and just see that your tangent line is always below your curve or a concave up, then your linear graph is always going to be under approximating. But then if the line is skimming the top of the curve, like a concave down graph, then you're always going to get an over approximation. So that's a common type of question that AP exams likes to ask, but again, if you can visualize it, then there's no need to memorize that. Now, we just have to be able to know whether something is underestimating or overestimating. We're not going to have to know, the accuracy of the overestimation or the underestimation. So we just have to be able to know whether it's under or overestimating. Okay, so let's look at number one. Let me give you a moment here if you're trying to. All right, so number one, our function is concave up. So we know our graph is going to look something like this. On this domain, and we have a set of information here about the graph. F of 4 equals 5 and f prime of 4 equals 3. What is the estimate for f of 3.8 using the local linear approximation for f at x equals 4? So whenever you see a local linear approximation, all you're trying to do is you're just trying to create a tangent line equation based off of what they give you. Okay, so anytime they ask you for estimate, don't worry about this 3.8 yet. Just build your tangent line equation first, based off of the data that is provided here. So our first task is creating that tangent line equation. So take your point, take your slope, and do point slope form. Even though this is in point slope form, we want to go one step further here. Just solve for y. And then once you have your tangent line equation, then you can worry about the estimate. So the estimate just means whatever your tangent line equation looks like, just go ahead and insert your decimal into the x of your tangent line. So we have y of 3.8 is equal to 3 times 3.8 minus 4 plus 5. Okay, now this unit you'll get to use a calculator. But I mean, if it was non-calculator section, you can just leave your answer in this form. You don't have to do all the math of adding and multiplying fractions. But this ends up giving us 4.4. So this is not the exact value. The exact value would be if I were to plug 3.8 into the original function, which we don't have any more data of what that function is. But all we have is the information for our tangent lines. So we know that our approximation of whatever the actual value is based off of our linear approximation is y equals 4.4. Now we know that our graph is concave up. So if our graph is concave up, then this approximation is going to have to be what? Underestimation, yeah. That's simply because of the fact that we know our graph is. Yeah. Reach here Monday? No. Okay, so underestimation. Since our function is concave up, the linear approximation will produce an under approximation. So this section of linear approximation is really, we're just doing the two things that you see in the name. This concept is linear approximation. So we're just going to do exactly that. We're going to form a line based off of our ordered pair and our slope. And then once you create our tangent line equation, then the approximation comes in plugging that decimal into the tangent line equation. And that's it. You're just creating your tangent line and then plugging the decimal. All right, here's number 2. The function f of x is concave down at x equals 1. Sorry, it's not a question mark here. That should be a statement there. Find the tangent line at x equals 1. So, okay, try that. Find your order pair. Find your slope from your derivative. Point slope form. And once you have your tangent line equation, then we can worry about the 1.1. Solve for y. We can use that to do our approximation. Okay, now we know what our graph is concave down. So as long as we know our graph is concave down, it doesn't matter where our tangent line is. This is going to be what? Over approximating, yeah. Okay, number 3, consider the differential equation. So I know this this sounds sounds complicated when you see that word differential equation. A differential equation is basically just a derivative equation. It's just an equation at the derivative level. And differential equation is just giving you information about slope, right? Sometimes they may have y's or x's in it, but it's basically just an f prime. So differential equation is just a derivative equation. Let f of x be a particular solution to the differential equation with the initial condition f of 2 equals 0. Write the equation for the line tangent to the graph of f at the point to 0. So your differential equation is your derivative. Your derivative can get you your slope. So you're going to take our ordered pair. We'll plug the ordered pair into the derivative to get our slope. And then we'll just do our point slope form. So it looks more complicated than other derivatives, but it's the same thing as derivative. So it just has x's and y's that's needed to build the derivative value. Okay, so we're just going to plug in 2, 0 into the derivative to get our slope. So 2 in for x's and 0 in for y's. So I get 4 times 2 is 8. 8 minus 10 is -2. -2 times 1 is -2. There's our slope. There's our ordered pair. Now we can create our tangent line equation. And then use the tangent line equation to approximate f of t equals 2. Y is basically by itself. If I move that 0 over, I mean, just drop the 0. So tangent line is just approximation is just 2.2 and for x. So I just want us to kind of recognize that this is an easy concept, right? We already know how to do our tangent line equation. So once we do that, then linear approximation is just whatever decimal they give you, just plug that in. It's literally just one step beyond your tangent line equation. Hey, we talked about particle motion, but we also want to talk about rate of change other than motion. Sometimes when we talk about first derivative or second derivative, our tendency is we want to think in terms of velocity or acceleration, but that may not always be the case. All right, page 6. So to know if something is increasing or decreasing, check the sign of its derivative. Height is increasing if h prime of t is greater than 0. And velocity is decreasing if v prime of t is less than 0. I'll show you the derivative on the calculator a little bit later. So right now, you just know that there is a feature in the calculator that allows us to evaluate the derivative at a point. But let me show that to you later. Is the function already a rate of change? So if if f of x is a bunny population after x years, then what is f prime? F prime would just be the rate of change of the bunny population per year at year x, whatever that x is. It could be the second year, it could be the third year, it could be the fifth year. But if they define f of x as already a rate, then what's f prime? Then f prime is going to be a rate of a rate. But typically, if you're talking about something at the second derivative level and it's not acceleration, first off, we don't want to say acceleration if it's not particle motion. And second, we don't want to say rate of a rate. It's not clear enough. What they want to see is they want to see something about the rate is increasing or the rate is decreasing to properly describe that second derivative. So we want to say that the rate at which the population is either increasing or decreasing depending on that f prime value. If f of x is already a rate, then f prime is either going to tell you whether that rate is increasing or that rate is decreasing. rate of change from a table. So if I want to estimate p prime of 15, then I'm just going to find the slope, right? So anytime that we want to find the slope, you want to choose the best accuracy that you can do, and that is the closest points possible. So if I want to find the rate of change at the 15th year, the closest order pair is involving 10, 120 and 20, 150. So we just find the slope using those 2 points. What if I wanted to estimate p prime of 20? What order pairs could you use? Yeah, but there are other options because it's right at that 20. So what was another option that we could do? Yeah, 10 and 20. There's actually one more that we could.
30.
Yeah, 30 and 10. So if something is exactly between, then you're forced into the 2 order pairs that's closest. But if there's some gray area, then you have a couple of options. And even though they all come out to be something different, technically you'll get full credit if there's that vague area where there's more than one interpretation. So I said between 10 and 20 and 20 and 30, but there's one more option. You can also choose using the 10 and 30. All right, a store is having a 12-hour sale. The total number of shoppers who have entered the store is defined by EFT. At what rate are the shoppers entering the store 5 hours after the start of the sale? So the rate is simply involving E prime. So we just plug 5 into the derivative, and whatever the derivative is, we just plug 5 in, and that gives us units in terms of shoppers per hour. Number 2, the function t equals f of p models the time and days for a small pond to evaporate as a function of size p, as the pond measured in liters, or the units for f double prime of p. So we have days, but then it's going to be at a rate measured in liters. So it's going to be the second derivative. So it's going to be, instead of days per liter, it'll be days per liter, or days per liter squared. Let's just do a couple of practice problems from page 7 and 8. Let's do number 2 and 4 together here. Number 2, for small positive values of h, cube root of 8 plus h is best approximated by. So here we want to create our tangent line equation, but we want to create a function that we can find the derivative for and find a nice point where we can create our tangent line equation. So there's a lot that's built into that. So if we remove that 8, our function is really just cube root of x, right? All this is kind of under the family of cube root of x. So that's our function. And then our x value is at x equals 8. And then think of the a plus h as the decimal value that we're going to plug in after we create our tangent line equation. So from here, see if you can build your tangent line equation. So plug 8 in to get your order pair, find the derivative, plug 8 in to get your slope, and then do point slope form. So just from this information, see if you can create your tangent line equation. And then we'll worry about the plus a plus or the h. Now, cube root, this is 8 to the 2/3. We can do this without a calculator because it's easier. You can cube root it before you square it. So do the cube root of 8, that's 2, and then 2 squared is 4. So we have all the data that we need to build our tangent line equation. And then solve for y. And then we're looking for some decimal value that is 8.2 or 8.3, but it'll just be a plus h. So all we need to do is our linear approximation part of this problem is just plugging that a plus h in for the x. And that will give us our decimal value that is some distance away from 8. And that's just going to match up with answer choice D. All right, try number 4. Use the tangent line to the graph at x equals 0 to approximate f of negative 0.3. So use the x equals 0 to find your order pair, find f prime. But just talk about briefly here, to find f prime, what process is needed here? Yeah, product rule. Yeah, so just keep in mind that product rule is going to have to be involved as you build your derivative. So find your order pair, find your point. So whenever you see a linear approximation problem, just don't worry about the decimal. Just focus your attention on, let's build that tangent line equation. Okay, find the derivative, find the slope, find your point, build your tangent line equation, and then that negative 0.3 will get plugged in. Okay, any questions with number 4? So we find the derivative using product rule, plug 0 in, we get slope of 1. But we have our order pair 0, 2. Once you build your tangent line equation, then your final step is to put that negative 0.3 in for the x, and whatever decimal you get, that's your approximation. Okay, for page 7 and 8, if you can go ahead and cross off number 1 and number 6. We're going to omit number 1 and number 6. Your homework is going to be just problems working around 1 and 6. So cross those out. And I like just to kind of get a head start into related rates. So let's go to page 9. Okay, so the main thing for this unit is related rates. I mean, we've done linear approximation. We're going to do some L'Hopital's rule. But these are all kind of minor topics that we're squeezing into this unit. But really, the big topic is related rates. So related rates kind of has a word problem feel to it. It kind of also has some resemblance to implicit differentiation because we have a bunch of variables that are now going to be dependent variables stuck inside our equation. So related rates are, this is page 9. Related rates are problems involving finding the rate of change with respect to time. So now time is the independent variable. And that is a bit of a change because up to this point, our independent variable has mostly been x. So when we find the derivative, it's always been with respect to x, right? So y prime of x, dy over dx. Those are all indicating that we're finding the derivative with respect to x. But now it's with respect to time. So now everything else is going to be a dependent variable. Everything else like y or x or length or height are all going to be a dependent variable. So this is an application of implicit differentiation, but what we're finding the derivative now is with respect to time. So everything is going to have a d over dt feel to it. So let me just run down these steps. We don't necessarily have to take these steps in this order. We just have to be able to take care of all these things eventually. So we want to write down what we're given. We want to write what we're trying to find. We want to write an algebraic equation that relates the variables together. So sometimes it could be Pythagorean theorem. It could be volume of a sphere. And then we find the derivative with respect to time. And then we substitute and solve. The derivative is going to feel more complicated in some sense because you have all these variables. But the good news is that mostly the derivative just requires power rule. There's not a whole lot of product, quotient, chain. So that's a nice thing. The variables make it look complicated, but really the derivative process is largely just power rule. All right, so here's example 1. The sides of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides measure 15 centimeters in length? So the first thing is we have to nail down what equation are we dealing with. So the theme here is area of a square. Okay, so that is our starting point. So area of a square is length times height, but the length and height are the same. So I'm just going to build my area equation. A equals length times length, or x times x. I'm going to just say a equals x squared. If x represents the length of my square, then area is just x times x, or x squared. I like to go ahead and find the derivative. That way we can see everything that's in front of us and we can start putting things together. Now, when you find the derivative, every variable is going to get impacted by time. So instead of just calling it a prime, it's now going to be dA over dt. Everything is now going to be over dt. Before, remember with implicit, you would make y into dy over dx. And dy over dx would mean that you're finding the derivative of y with respect to x. But now every variable is going to get touched by time. So x squared, always find the derivative of what you see in front of you. And then we'll worry about the conversion or the adjustment later. What's x squared's derivative? 2x, okay. But we're asking for x's derivative with respect to time. So guess what we need to attach? The x over dt. So every variable is now going to have this time derivative component attached to it. So area is going to get it, x is going to get it, and everything else. But those are the only two variables, so we can stop there. Now, what does dA dt represent? dA dt represents the rate of change of area with respect to time. So let me just write that out so we can be able to say it. So this is the rate of change of area with respect to time. And then dx over dt represents the rate of change of length x with respect to time, or in relation to time. All right, so let's go back and read the problem and see if we can start to assign these values to variables. The sides of a square are increasing at a rate of 5 centimeters per minute. So we know that the sides is in terms of x, but there's a movement involved, right? There's a rate involved. So anytime there's a time component, you know that it's got to be something over dt. So if I'm trying to describe the rate of change of the side here, guess what that 5 centimeters per minute is going to represent? Which one? Is it dA dt? Is it x, or is it dx dt? Dx dt, yeah. So it's going to represent this piece here. So let me go ahead and just label that. Dx dt is just 5 centimeters per minute. How fast is the area increasing? So guess what this is referring to? dA over dt, yeah. That's the unknown. So that's what we're looking for. That's going to be the question mark that we're looking for. When the sides measure 15 centimeters in length. What can we assign 15 to be? X. X is 15. Okay. And now we just put everything into its place. dA dt is the unknown, so we'll leave that as a variable. 2x. We know x is 15. And then replace x dt with 5 centimeters per minute. So now this tells us that at this moment in time, the area is increasing by this amount. So 30 times 5 is 150. Now, another important skill is building your units. And we have two units here, area and time. Area is in terms of what? Centimeter square. So you're going to put that in the numerator. Time is in terms of a minute, so that's in the denominator. So it's going to centimeters squared per minute. If you're ever having trouble with your units, look at the variables involved and then see if you can assign the variables, the units for each variable, and then just put them over each other. Okay, we're just getting a head start into it. We'll tomorrow is really the full day that we're going to devote to related rates, but just getting head start, I think is going to be good for us. So your homework tonight, pages 5 through 8 all, but you're also omitting the ones that I crossed out, right? You're crossing off number 1 and 6 on page 7 and 8.
So,